The year is 1962, and the IMO is being held in Czechoslovakia. One student, Iosif Bernstein from the USSR, participates and gets a perfect score. Amazing. So today, we're going to try to channel some of our inner Iosif Bernstein and take on problem 2, which was proposed by Hungary from the 1962 IMO competition. Gives us a bit of a messy function with square roots and asks us simply to determine where the function is greater than 1/2. There's going to be a lot of algebra we're going to have to do for this problem, which takes quite a long time to be explained and written out carefully, but the ideas aren't too complicated. Oh, my coffee's ready.
Coffee Time Math with your host, Wrath of Math.
There is nothing I'd rather be doing right now than solving this problem with you. Let's do it. All right. I've got this beautiful water fountain going for us to lull us into a sense of security, although it might be the last time you see it, depending on how much the microphone picks up its sound. I don't think it'll be a problem, but we'll see. You let me know what you think. So what are we doing today? Well, we've got this function, square root of root 3 minus x minus root x plus 1, which we'll call f of x occasionally during our time together. And we want to know for what values of x is this function greater than 1/2? That's what we want to know. Once more, for what values of x is this function greater than 1/2? Now, I like my coffee black, but if that's not how you like your math problems, here's some cream and sugar on screen now. Hints to try this problem out yourself. A reasonable place to start before we figure out where's the function greater than 1/2 is, let's get a little less specific for starters. Where's this function even defined? For what values of x is this function defined? What is its domain? Well, the things that are going to cause us problems are all these square roots. Of course, we need the stuff underneath square roots to be non-negative, because we can't be taking square roots of negative numbers. So let's go step by step through these different square roots, see the inequalities that we get, and what restrictions are forced on x. For starters, the square root of 3 minus x. 3 minus x, of course, has to be greater than or equal to 0. Adding x to both sides yields x has to be less than or equal to 3. All right? Next, we've got the square root of x plus 1. Of course, x plus 1's got to be greater than or equal to 0. X plus 1 is greater than or equal to 0. Subtracting 1 from both sides yields that x has to be greater than or equal to -1. And let me just redraw that arrow, because that looked a little bad. There we go. X has got to be greater than or equal to -1. And then finally, we've got the big square root. Everything underneath the big square root has got to be greater than or equal to 0. So the square root of 3 minus x minus the square root of x plus 1 has to be greater than or equal to 0. That would mean that the square root of 3 minus x has to be greater than or equal to the square root of x plus 1. All right, now let's go ahead and square both sides of this inequality. That would give us that 3 minus x has to be greater than or equal to x plus 1. All right, that's not so bad. We'll add x to both sides and subtract 1 from both sides. That gives us that 2, which is 3 minus 1, has to be greater than or equal to x plus x, or 2x. Thus, dividing both sides of this inequality by 2 and writing it in the opposite order yields that x has to be less than or equal to 1. Now, make sure you are comfortable with this string of inequalities, because I'm going to now erase them and just write the one that matters. X is less than or equal to 1, just so that we have some more space to work with moving forward with the rest of this problem. So this restriction, the fact that this stuff needs to be greater than or equal to 0, and thus the square root of 3 minus x is greater than or equal to the square root of x plus 1, forces this restriction on x, that it's got to be less than or equal to 1. So originally, we saw that x had to be less than or equal equal to 3, now we see things are even a little bit more strict than that. X has got to be less than or equal to 1. But as long as x satisfies all of these inequalities, we're good to go. The function will be defined, and so our function is defined when x is in the closed interval from -1 to +1, because x has to be greater than or equal to -1, and the strictest restriction on the other side is that x has to be less than or equal to 1. For any other real number, or excuse me, for any real number between -1 and 1, including -1 and +1, for any of those real numbers, this function will be defined. So now we know that this is the domain of our function. We want to figure out where in the domain is our function greater than 1/2. A question we might ask is our function ever exactly equal to 1/2? That would get us a little closer to our solution. Turns out it is, and we can conclude that by the intermediate value theorem. Let me show you precisely what I mean. We know the endpoints of our domain are -1 and 1. What are the actual endpoints of the values that the function's taking on? As in, what is f of -1 and f of +1? I don't know. Let's figure it out. So I'll just draw a line here to separate some of our work. Let's plug -1, the smallest number in the domain, into our function. F of -1 is equal to what? Well, it would be the square root of the square root of 3 minus -1. 3 minus -1 is 3 plus 1. That's 4. So that's the square root of the square root of 4 minus the square root of x plus 1. X in this case is -1. That's going to be -1 plus 1, which is 0. That's the square root of 0. All right, so what's this equal to? Well, the square root of 4 is 2, minus 0 is 2, so then we just got the square root of 2. Wonderful. So f of -1 is the square root of 2. That's the first value that our function takes on. What about the last value, f of +1? That's the other endpoint in the domain. Well, we of course have our big square root. Then we've got the square root of 3 minus x. 3 minus 1 is 2, so that's the square root of 2 minus the square root of 1 plus 1. That's also 2. So this is a square root of root 2 minus root 2. That's the square root of 0. And that, my friends, is 0. Now, we know that our function is continuous, right? Because it's just the square root of stuff. And as long as the square root is defined, which it is in this closed interval, it is continuous. So maybe our function looks something like this. Let me draw an extremely rough sketch, because right now we're not doing any work to get an idea of what our function really looks like. So the idea is we have no particular clue what our function looks like at the moment, so we just draw arbitrarily looking something like that. It starts at this square root of 2 value, where x is equal to -1, and then where x equals 1, our function takes on a value of 0. Besides that, we just know that our function is continuous. So the main idea is that since the function is continuous on this closed interval from -1 to 1, and at the beginning of that interval, our function takes on a value of root 2, and at the end it takes on a value of 0, the function must take on every value between the square root of 2 and 0 at some point in this closed interval. 1/2 is, of course, between the square root of 2 and 0, so at some point our function must take on the value 1/2, and that is what the intermediate value theorem tells us. So maybe our function is equal to 1/2 right there. Once more, the intermediate value theorem tells us if a function is continuous on some closed interval, and say that on one end of the interval the function's equal to square root of 2, and on the other end the function's equal to 0, then the function must take on every value between the square root of 2 and 0 at some point in that closed interval that it is continuous on. So at some point we know that our function is equal to 1/2. Then some other useful information would be, is our function increasing or decreasing? Because if it's either of those things, well, that would be pretty useful, right? We know immediately that our function can't be increasing because at the beginning of its domain it's at the square root of 2, and at the end of its domain it's 0. So if anything, it's decreasing. If it's decreasing, that's really useful because then we know wherever it hits 1/2, it must be greater than 1/2 everywhere in its domain that precedes the point that it's equal to 1/2, because it would be decreasing. So it's just going down and down. Wherever it hits 1/2, maybe your function looks something like this, and maybe that's 1/2. Wherever it hits 1/2, it's going to be greater than 1/2 everywhere before that point if it's decreasing. So let's see if we can figure out if the function's decreasing. Once more, we know that it can't be increasing, but if it's decreasing, that would be really useful. Because if it isn't decreasing, we don't know if it does something like, it's greater than 1/2, then it hits 1/2, then it's greater than 1/2 again, then maybe it hits 1/2 a second time, then maybe it's greater than 1/2 some more. It could be some really nasty union of intervals if we can't confirm that this function is decreasing. So let's get this out of the way and see if we can sort this all out. Let's take the red marker. Let's address this function piece by piece to try to figure out what's going on here. Consider the square root of 3 minus x. Is the square root of 3 minus x increasing or decreasing? And remember, when we say increasing or decreasing, we're talking about what happens as x gets larger. So if as x gets larger, the square root of 3 minus x gets smaller, that would mean the function is decreasing. If as x gets larger, the square root of 3 minus x also gets larger, that would mean that it's increasing. In this case, the bigger that x gets, the more we're subtracting from 3. So the smaller this number gets, and thus the smaller its square root gets, and so indeed the square root of 3 minus x is decreasing. I'll just say DECR for decreasing. What about this other part, square root of x plus 1? Square root of x plus 1. Here, clearly, as x gets bigger, x plus 1 gets bigger, and so its square root gets bigger. So this part is increasing. I'll just write INCR. So what does that mean about our whole function, this big square root? Well, we've got the square root of 3 minus x, which is decreasing, and then we're subtracting a bigger and bigger amount from it because root x plus 1 is increasing. So the whole function must, in fact, as we so desire, thankfully, be decreasing. Once more, that's because this whole thing, this expression, the radicand, is getting smaller because the square root of 3 minus x gets smaller and smaller, and we keep subtracting a bigger number from it because the square root of x plus 1 is increasing. So this is getting smaller and smaller, so its square root is getting smaller and smaller, so the function is decreasing. Remember why that's super important. We now know that at some point the function is equal to 1/2. Since the function is decreasing, it must be greater than 1/2 precisely at all those points preceding wherever it hits 1/2. So we've reduced the problem to this. Figure out where the heck this function's equal to 1/2. So again, remember by the intermediate value theorem, that's how we know that our function is equal to 1/2 at some point. So it makes sense to write this equation. This equation does have a solution. And since our function's decreasing, this actually has exactly one solution that we are interested in because the function's decreasing. So once it hits 1/2, it's just going to get smaller and smaller. It's never going to hit 1/2 again. If we can find where it's equal to 1/2, since it's decreasing, it must be greater than 1/2 at all the values preceding the point where it's equal to 1/2. All right, let's cruise. Let's solve this equation. So for starters, let's get rid of our giant square root, square both sides of this equation. That's going to give us that the square root of 3 minus x minus the square root of x plus 1 is equal to 1/2 squared, which is 1/4. I'll also mention, this is the point of the problem where nothing else we have to do is super hard, but there's lots of it that we have to do, and it's very easy to screw up all of the algebra. All right, now we would like to square things again to get rid of these radicals that we have going on, but let's add the square root of x plus 1 to both sides first so that we don't get the square root of 3 minus x times the square root of x plus 1. We don't want to deal with that. So let's add that to both sides. That's going to give us the square root of 3 minus x is equal to 1/4 plus the square root of x plus 1. That's what we added to both sides. Now, if we square things now, that would be fine enough, but the fraction's going to make things start to get kind of ugly. We don't want to worry about getting common denominators. I'd rather work with larger numbers. So let's just go ahead and get rid of this fraction by multiplying everything by 4. Doing that's just going to pop a 4 in front of this bad boy. It's going to turn the 1/4 into a 1, and it's going to pop a 4 in front of this bad boy, just multiplying everything by 4. Now, let's go ahead and square both sides of the equation. If we square this on the left, that's going to give us 16 multiplied by 3 minus x. Then, of course, you should be pretty comfortable squaring binomials. If we square this expression, we're going to get 1 times 1, which is 1. We're going to get 1 times 4 root x plus 1 plus 4 root x plus 1 times 1. That's going to be 2 copies of 1 times 4 root x plus 1. That's just 8 root x plus 1. And then we're going to get 4 root x plus 1 squared. That's going to be 16 times x plus 1. And you're like, man, we got another square root we got to get rid of. Got to do what you got to do. Before we square all of this again to get rid of this last square root, let's go ahead and bring everything except the radical expression to the left side of the equation to make sure that this is on its own, so that when we square everything, we get rid of that radical once and for all. So let's start to combine some of these terms and all that. 16 times 3 is 48. Then we would subtract 1 from both sides, making that 47. Then we would subtract 16 from both sides, making that 31. So our constant term on the left is 31. 16 times minus x is minus 16x. Then we would subtract this 16x, which is going to give us minus 32x. So that's 31 minus 32x. On the right side, all we'll have left is 8 times the square root of x plus 1, and now we are ready to square it all. I hope you can understand that at some point we need to start saving some room. Now is that point. So here's what we've got. 31 minus 32x is equal to 8 times the square root of x plus 1. Then we square both sides of this equation to get rid of that radical once and for all. Squaring both sides of the equation gives us 32 squared times x squared plus 2 copies of 31 times minus 32x plus 31 squared is equal to 64x plus 1. Beautiful. Then 32 squared is 1024, so we've got 1024x squared. 31 times 2 times minus 32 is minus 1984, so we've got minus 1984x. And then 31 squared is 961, that's why we've got that plus 961. And then we just distribute the 4. So on the right side of the equation, we have 64x plus 64. Then we just want to subtract the 64x and the 64 from both sides of the equation. So we've got everything on the left side equal to 0. We've got a quadratic equation we can solve with a quadratic formula. So finally, we have 1024x squared minus 1984x minus 64x. That's minus 2048x. Then 961 minus the 64 leaves us with 897. That's all equal to 0. Now we can apply the quadratic formula to solve for x. We've got negative b. In this case, b is minus 2048. So negative b is a positive 2048. Plus or minus the square root of b squared, which is minus 2048 squared. The negative squared is going to be positive, so we don't have to write the negative. Then minus 4ac. A is our leading coefficient, 1024. C is our constant term, 897. This is all divided by 2 times a. A is 1024. 2 times 1024 is 2048. So this is the quadratic formula application that we can now use to get our answer. I'm going to go ahead and write this purple equation on the board. Beautiful, isn't it? We've got x must be equal to 2048 plus or minus the square root of 2048 squared minus 4 times 1024 times 897 all over 2048. Now this is an IMO problem, so we got to solve it without a calculator, which makes this look a little bit intimidating, but if you've seen enough math and you're familiar enough with your powers of 2, you may notice there are a lot of powers of 2 going on here, so we may actually have some luck doing some simplification. Let's just list off powers of 2. I'll count the exponents with my fingers. 2, 4, 8, 16, 32, 64, 128, 256, 512, 1024, that's 2 to the power of 10, 1024, and then one more, doubling 1024 is 2048. That's 2 to the power of 11. So let's go ahead and rewrite some of this stuff in terms of powers of 2, and that's going to simplify our job quite a bit. Sorry I had to switch colors because the purple seems to be totally gone, so here we go. 2048, that's 2 to the power of 11. Then we've got plus or minus our big square root. Here we have 2048 squared. Remember, 2048 is 2 to the power of 11, so that's 2 to the power of 11 squared. Minus 4, which is 2 squared, times 1024, which is 2 to the power of 10, times 897, which I have a feeling is not a power of 2. Then that's all divided by 2048, which is 2 to the power of 11. All right, there's some more work we can do here. We could rewrite this expression as 2 to the power of 11 divided by 2 to the power of 11 plus or minus the rest of the stuff. This over 2 to the power of 11. 2 to the power of 11 over 2 to the power of 11 is equal to 1, so this would just leave us with 1 plus or minus the rest of the stuff. The rest of the stuff is the square root of 2 to the power of 11 squared, which is 2 to the power of 22, minus 2 squared times 2 to the power of 10. We can just add the exponents to combine that to get 2 to the power of 12 times 897, and then all over 2 to the power of 11. Now we're going to have to jump over this blue part of one of our previous equations in order to continue our long orange equation. Big question now, are there any squares that we can take out of this radical, that we can take out of this square root? Yes, there are. Here we've got 2 to the power of 22. Here we've got 2 to the power of 12. So of course, this 2 to the power of 22 also has 12 factors of 2 within it. 2 to the power of 12 is a perfect square. What is it the square of? Well, 2 to the power of 12 is, of course, the square of 2 to the power of 6. If you square 2 to the power of 6, you get 2 to the power of 12. Since 2 to the power of 12 is also a factor of 2 to the power of 22, we can factor that perfect square out of these two terms and out of the radical. So what's that going to leave us with? It leaves us with 1 plus or minus, factoring out the perfect square 2 to the power of 12 would leave us with 2 to the power of 6 multiplied by what we've got left in the square root. We took 2 factors of 12 out of both terms. That leaves us with 2 to the power of 10 minus 897, because we took all 12 factors of 2 out of the second term, and then this is all getting divided by 2 to the power of 11. Now, of course, we can bring the 2 to the power of 6 down to the denominator by subtracting its exponent from 11, because we've got the same bases here, so we can just subtract their exponents to bring 2 to the power of 6 down to the denominator. So let's finish this job off. This is equal to 1 plus or minus 2 to the power of 11, and then we're going to subtract that exponent of 6, giving us 2 to the power of 5. What's 2 to the power of 5? 2, 4, 8, 16, 32. So let's just go ahead and write that denominator as 32. Then in the numerator, we have 2 to the power of 10, which we've said several times, is 1024 minus 897. What is 1024 minus 897? That would be 127. So we'll go ahead and erase that and rewrite it as 127. Fantastic. So these are the solutions, right? 1 plus or minus the square root of 127 over 32. That's where the function is equal to 1/2. But wait a minute, you might think, didn't we say there should only be one solution? Yeah, there's only one solution. we're interested in. The problem is we squared the equation a couple times, which has the potential to create additional solutions. Just like, for example, x equals 2 has only one solution. But if we square both sides of the equation, we get x squared equals 4, which has two solutions. So here we've got a solution that we don't care about. Which one is it? Is it 1 plus the stuff or 1 minus the stuff that we do not care about? Well, remember, the domain of our function is the closed interval from -1 to 1. So we certainly don't care about anything that's greater than 1, as in 1 plus stuff. We don't care about that. So let's just get rid of that. We're only interested in 1 minus the stuff. So our function is equal to 1/2 at x equals 1 minus the square root of 127 over 32. That means whenever x is in this domain, but before it hits this particular value, our function will be greater than 1/2 because the function is decreasing. So as long as x is between -1, and it can also be equal to -1, but less than this, our function will be greater than 1/2. Let me go ahead and write it. So since our function is decreasing and starts at the square root of 2, which is greater than 1/2, our function will be greater than 1/2 at all values in its domain up until x equals 1 minus the square root of 127 over 32, not including 1 minus the square root of 127 over 32, because that's where our function is equal to 1/2. We're not interested in that. We're only interested in where it's greater than 1/2. So once more, what's the answer to our question? This function is greater than 1/2 for all values of its domain that are less than 1 minus the square root of 127 over 32. And that's it.
The end.
Subscribe for more of the swankiest math videos on the internet.